Good evening, BMB510, MNE525 class. So we're going to finish up what we were talking about on Tuesday regarding fluid dynamics. And we were talking about, when we knocked off on Tuesday, we were talking about flow of saline into a catheter to flush out blood. And then I was just about to talk about plug flow. So we've talked about laminar flow, and we've talked about that parabolic flow profile where the flow, the velocity at the center line is the highest, and the velocity at the tube walls is zero. Plug flow is a bit of a different thing, where plug flow is just this flat flow profile, and you can see down here in the bottom that the velocity throughout the inner diameter of the pipe or blood vessel is basically the same. It's all the same. Fully developed flow of fluids will take the parabolic, Poisson, whatever you want to call it, this flow profile, this parabolic flow profile, and that's laminar flow. Plug flow is that flat flow profile, and the flow of many fluids will initially start this way. So this plug flow is a transient sort of flow profile that will happen. So again, let's consider blood flush from a catheter. We have a 1 ml catheter that's initially filled with blood, and at time t equals 0, the catheter is flushed at a constant rate, and that rate is 1 milliliter per second with our saline. How long is it going to take to flush out 99% of the blood, and how much saline will we need to do this? This time, unlike last time, we're going to assume that the fluids will not mix. So we will keep the densities of the fluids separate. We won't have to have this density of the fluid mixture like we did in the last example. And so essentially we can consider a plug flow profile for this, where we have our catheter. The flow profile will be flat. And how long is it going to take for, in this flat flow profile, to flush out 99% of the blood that's in this catheter? How much saline are we going to need to get 99% of that blood out? And again, remember that the saline and the blood aren't mixing in this scenario. So, this is a much simpler answer than our first example. So because the saline is just going to push the blood out of the catheter, and all of the blood will be pushed out. Since it's being flushed at a rate of 1 ml per second, we've got a 1 ml catheter filled with 1 ml of blood. All the blood will be gone after a second. The saline will have pushed it all out. 99% of the blood is going to be pushed out after 0.99 seconds. And so again, it's as simple as that, because plug flow is blood is simply being pushed out at a constant rate. And so to push 99% of the blood from the catheter, what you need is 9.99 milliliters of saline. So, and that simplifies this problem quite dramatically, as we can see here. Not saying that this is what would happen, but just imagine if we're talking about two fluids not mixing. Obviously saline and blood are going to mix. So this is just really a thought experiment. So what about laminar flow? We talked a little bit about turbulent flow. We talked about Reynolds numbers and turbulent flow. But what about laminar flow? So if saline is flowing into the blood-filled catheter by laminar flow, then calculations get a little more involved. Blood will first be pushed out, and again, this is if they're not mixing. Blood will be pushed out in the center, and then later on the sides close to the wall. So that if this is not plug flow pushing the blood out, instead it's laminar flow pushing the blood out. You know, this blood in the center line is going to be pushed out first, as you can see, and then lingering effects, lingering blood will be at the walls there. Again, still a thought experiment, because, you know, as we can imagine, we're going to get mixing of the saline and blood. In the end, saline pushing the blood out of the catheter and not mixing with it in terms of laminar flow, more volume will be required, due in part to that, if we're talking about a laminar flow profile, low velocity at the catheter walls. So the final equation will look like this. The volume required to flush is equal to QVT star, which is 25 times the volume. The volume in our case is a 1 mil volume. So 25 milliliters of saline will be required. And this is the volumetric flow rate, again, multiplied by the T star, the time it'll take to flush out the catheter. Okay, so let's go back to just thinking about flow of a fluid in a conduit. So when we're talking about fully developed laminar flow, friction happens. That's why we see the parabolic flow profile, because we have friction terms and resistance at the walls of the tube or the blood vessel or whatever it is. So we need to consider that. One thing we can do is use the fanning friction factor, which is used to account for friction losses in straight conduits. And generally a friction factor can be defined for flow past a stationary body or flow through a stationary conduit, which in this case is what we are considering here. But in either case, the fluid will exert a frictional force on a stationary object. And the friction factor can be defined by this relation right here. Fk is our kinetic force applied to the conduit that fluid is flowing through, or to the object the fluid is flowing over. K is the mean kinetic energy per fluid volume. A is the characteristic area. And F is this fanning friction factor. In the case of flow through a conduit, the term A is the wetted surface area of the conduit, which can be called SW. SW is the product of the wetted perimeter and the length of the conduit. K is 1/2 the average velocity and the density. Thus, for the fluid in a conduit, the friction factor can be calculated with this equation here. So where we consider the kinetic force, and we can either have the wetted perimeter on the bottom half, or we can have the wetted surface area. Here's the wetted perimeter times length, and here's the wetted surface area right here. And then this whole 1/2 PV squared is actually the K term that we saw in our original equation. And this is all solved for F, that fanning friction factor there. The kinetic force can be found from a macroscopic force balance on fluid within the conduit. So we look at that pressure drop here. We have Fk as our kinetic force. We look at the pressure drop P in minus P out times AC, which is the cross-sectional area of the fluid within the conduit, plus the density of the fluid. Again, that times we've got a cross-sectional area term here, times the length of the conduit, times Gx. And Gx is related to the height difference between the inlet and outlet flow. So this height difference here is where Gx is coming into. So the kinetic force is here, and from below we can calculate to get a different term for Gx here, where we have the equation here. We can remove, since AC is in both of these terms here, we can take that out, and we have the pressure drop plus the density times G multiplied by the difference in height, H in, the height at the inlet, minus the height at the outlet. And we can think about the hydraulic diameter of a conduit, which is, again, the cross-sectional area times 4 divided by the wetted perimeter, or the cross-sectional area times 4 multiplied by the length of the conduit divided by the wetted surface area. So let's look at that in an example, the pressure drop across bronchi in the lungs. So bronchi that are located 2 generations down the respiratory tree from the trachea have a mean diameter of about 9.4 millimeter, and a length of about 30.3 millimeter, or 3.03 centimeter. And you can see we're talking 2 generations. We have the primary bronchi, the secondary bronchi are coming up, branched off of that, and then you have tertiary bronchi that are branched off of that. And that's what we mean by 2 generations down the respiratory tree. If airflow during inspiration is 1 liter per second, so our QV is 0.25 liter per second per bronchus, estimate the pressure difference at delta P across these bronchi. So we want to find delta P, the pressure drop. So in the bronchi, QV is equal to 0.25 liter per second per bronchus. The bronchial diameter, D, equals 0.94 centimeters. Calculate the average velocity in a second generation bronchus using this equation here. And 1 mil is equal to 1 cubic centimeter. So we can do that. We can plug everything in. You know, we have Q, and we just change the units a little bit. And then we have the diameter. So we get 360 centimeters per second is the average velocity. The Reynolds number in each of these 4 bronchi is 2,155. So we can determine the friction factor. We have the Reynolds number here. We can determine the friction factor using this thing called the Moody diagram. So a special application of the Moody diagram includes a laminar flow in which a circular in a circular tube, where the friction factor is equal to 16 divided by the Reynolds number. So in this case, F equals 16 divided by 2155, our Reynolds number, is equal to 0.0074. So we have F equals to 0.0074, and this isn't including entry effects. So to do this, we must consult this graph here. And you can see this is basically 4F times L over D on the y-axis, and 1 over the Reynolds number times L over D in the x-axis. So since L is equal to 30.3, D is equal to 9.4, and RE, Reynolds number, is equal to 2155, what is our x-axis coordinate? It is 0.0015. So we look for that on the map, on the graph rather, and then we follow it and get our F, our new F, that includes entry effects. The friction factor now is 0.0388, which is about 5 times higher than what was estimated if entry effects weren't included. So from this, we know our friction factor with entry effects, F equals 0.0388. Our length of the conduit that we're interested in, the bronchi, 3.03 centimeters. The diameter is 0.94 centimeters. And the average velocity is 360 centimeters per second. Additionally, density of air is right here, 1.1 times 10 to the negative third grams per centimeter cubed. So we want to determine our pressure drop in centimeters of water. And a conversion for that is 980 grams per centimeters second squared centimeter of water here. And we can determine it via this equation here, this pressure drop equation. So we do that, we plug in the numbers because we have these numbers here. We have them all. We get 0.036 centimeters of water. And that's essentially it. So there will be an assignment posted, hopefully tonight or tomorrow. So please look at it and feel free to contact me with questions, and I will see you on Tuesday when we will get into some case studies in bioengineering. Have a good weekend.